All right, so here are the standings for the first 2 weeks. Once again, we'll rack it up as in first place, no change there. We had some big movers. The big mover Stack and Racks jumped up 1, 2, 3 spots up into number 2. And CD's Nuts dropped 3 spots into way down there somewhere. And there are a few others that moved a couple spots up or down. And then the big 3, I guess that is, and Rack-Eyed CDs are still at the bottom. And Rack-Eyed CDs actually managed to dip below $800,000 in net assets. So they are now losing money rather than making money. So this was price versus sales for this period, shown by team. So each color, each symbol represents a different team. Some teams, so basically anything at 80 or above, I plotted here. Some teams had big back orders to deal with, so that explains some of that, I guess. A better graph is to show price versus sales for period 1 and period 2. So the orange dot, that was from last week, price versus sales. And the blue are from this week. So we can see that the sales are generally higher than they were last week. And the prices are generally higher as well. So it's kind of interesting. Not sure why that is. But competition does drive a lot of it. I think I did that plot right anyways. So again, stock price versus assets. Again, there's a pretty strong correlation, as you might expect. Okay, so overall results. This is the industry report. Just trying to point out some notable things. Worldwide prestige is by far the lowest on cash. Not sure why that is. We do have a couple of construction projects ongoing. I looked at the raw materials inventory. I'm not sure why I highlighted those. I guess I should have highlighted these guys here have 74,000 units. Oops. This is in dollars though, $74,000 worth of raw materials. So these guys have a lot of raw materials. These guys have a fair amount, and then some teams have 0, or one team has 0, which is fine. You can always buy more. Our leading team has a modest supply. Earnings per share, so Stack and Racks made a huge amount of money this period, which obviously explains their leaping up 4 spots. Actually had negative earnings per share, meaning they lost money. CD's Nuts and Miracles. We have our first dividend. So Disco has a dividend pending. And we have some insider trades pending. Note that these won't be executed until period 3. And they're all pretty simple, just teams buying shares in themselves. One last thing, we'll look at the sales. The big 3 sold over 11,000 units. And Rack and Roll sold almost 10,000 units. Seems a bit excessive. We had a couple teams selling 0. I'm guessing they were trying to deal with back orders. And then other teams selling kind of reasonable numbers. All right, so this is period 2 of the game. Period 3 of the game is this coming week. Period 3 is the last round of the practice round. So after next week, we'll start the real round. So this is the last period of the practice game. So if you have any end game strategies you'd like to try out, now would be the time to do it. Right? Okay. Any questions about the game? Okay, hearing none. We'll jump right into today's lecture. All right, so this is the first lecture with kind of a specific application area for like optimization in business. I call it depot location. Probably a better term would be facility location. That's the more standard terminology. And in the case of this game, you might think of where should I locate my plants? Is kind of the main issue we're trying to address here, or perhaps warehouses as well. Okay, so we're going to look at a few kind of standard problems in this genre. Given a network of nodes which represent customers, so think of dots on a map or cities on a map, where each city has a demand, and we know all the distances between all the cities. Determine the optimal node or city to locate a depot. So we'll probably start with locating one depot or one plant, and then we'll talk about locating more than one plant. And in this analysis, we're going to assume that the only possible locations of the plants is at the cities that the nodes or cities that we have in our problem. So if this was if we were solving a problem in the game, we'd have to locate the plant at one of our 12 cities, which is in fact true in the game. All right, so our objective function is to minimize the weighted average distance between the depot and the customers. And when I say weighted, it's weighted by demand, right? So it's the demand at a city times the distance between that city and the depot, and you add it up over all the cities. All right, so you kind of draw a picture like this. We have several cities represented by blue dots. The size of the blue dot indicates how much demand there is at that city. The red square represents the depot. So we have the distance from the depot to all the cities. So we take those distances, multiply by the demand, and add them all up. Right? So if S sub I is the demand at each customer or city I, and Dij is the distance from city I to city J, then if I take S sub I times the distance, that's called the demand weighted distance. All right? And we want to minimize the sum of these demand weighted distances, where J is where the depot is located. Okay, so minimizing demand weighted total distance has lots of applications. The main one being exactly what you think, locating plants in transportation distribution applications. There are other applications as well, but they're probably not worth talking about. When you have a single plant you're trying to locate, it's called the median problem. My phone going off. So there are some situations in which you can show that there is an optimal solution where the plant lies at one of the nodes and rather than in between the nodes, right? So you might ask, why are we not considering a location that's somewhere in between the nodes? That basically, if this property, the Hakimi property holds, you only need to consider the cities. I think I didn't say that exactly right. Sorry. If you're considering the nodes or the cities and the arcs that link them, consider like the roads between them. If you're considering locating the plants anywhere on those links or nodes, on those cities or roads between them, then you can always find an optimal solution where the plant lies at a city and therefore you don't have to consider the roads. There could be somewhere that's off of the roads that's better. Okay, so with one plant, it's called the median problem. If you're going to consider more than one plant, if you're going to consider locating P plants, it's called the P median problem. Okay, so we'll start with the single plant problem. This one is pretty easily solvable in Excel. Let me go over there. Oops, come on. Let me try again here. Okay, give me one more chance here. Why can't I do this? Okay. Okay. So here's a very simple example. We're trying to figure out where to put one plant. So what we start with, these are just the distances between all the cities. That's our distance matrix that we posted at the very beginning. And these are the demands. All right. So demands in each of these cities up here. Now, one of the assumptions we're making here is that we know what the demands are. Obviously, that's a shortcoming because, you don't really know what the demands are, but we're assuming we know what they are. So we can just create a matrix of the demand weighted distances. So for example, this node here, this number here, it's just the demand, 575 times the distance, 1382, right? So just multiply demand times all of these distances and we get the demand weighted distances. Okay. These are the demand weighted distances between all the cities. And if you simply add up a row, that's the sum of this row. That'll tell you how much it would cost in terms of demand weighted distance if we located our plant in Chicago. And we just add up all the rows and we can find out which one is the cheapest. So if we look at all the numbers, the cheapest place to locate our plant is Nashville, all right? And the most expensive seem to be Seattle, LA, and San Francisco, right? Now, granted, these are based on the demands we assume. If I change the demand in LA, so 429, 240, if I change that to 7,000, these numbers all change. And now the cheapest is probably going to be Los Angeles, as you might guess, right? All right, so that's finding the best location for a single plant is pretty easy. You just try them all out, right? Try locating a plant in each city, calculate the cost for each city and pick the cheapest. All right, so the next thing we're going to do, this is something you might want to do in the game. So, I have this right? All right, so assume we have a plant already and we want to consider where should we put the second plant. All right, so let's assume we have a plant in Nashville. All right, and so we can take the demand weighted distances from Nashville and copy them in here. And now suppose we wanted to consider locating a second plant in Boston. All right, so we take the demand weighted distances from Boston and we just copy them down here. And then now that we have two plants, right, then you could say the following. Okay, given that I have 2 plants, where should I supply Chicago from? So you just look at these 2 numbers and pick the cheapest, right? So the cost is going to be, for each column, it's going to be the minimum of these 2 numbers. And whichever one is the minimum will also tell us from where we're supplying each customer, right? So all these ones mean that the minimum was from Nashville, right? The one here means that Boston is closer. So we're supplying Boston from Boston. We're supplying Washington from Boston, and all the rest are coming from Nashville, all right? And if we add all of these costs up, that'll be the total cost of supplying our customers. Does that make sense? So we have a plant in Nashville, have a plant in Boston. We just pick whatever one is cheaper and then add up the total cost. So that'll tell us the cost of having a plant in Boston and Nashville. All right. So I don't know this part here. I don't know why I should have deleted that. That was from an old example. We're going to go down here. And what we want to say is, okay, given that I have a plant in Nashville, where's the best place to locate a second plant? So basically, I got to do that minimum thing. So basically, if you look here, I have a minimum statement, right? And so basically, this is going to pick the minimum of the weighted distance from Nashville and Chicago. So I double click on that. You can see it's taking the minimum Nashville and Chicago for the city of Miami, right? So, I mean, if we place our second plant in Chicago, these will be the distances. And I add them up, and that gives me the sum. Okay, now I can just go down this column and find out where is the smallest number. And the smallest number in this case is Salt Lake. So this answers the question, given that I have a plant in Nashville, where should I build my next plant? And the answer is Salt Lake. Again, assuming that these are the demands that we're incurring. All right, can you see my presentation now, Sachio?
Yes.
Okay, thank you. Okay, so we considered these 2 problems already. Where's the cheapest place to put a plant? And then given that we have a plant, where do we put the next one? Let me ask you this question. Suppose that I wanted to find the best 2 cities to build a plant in. Will the procedure I just went through give me the best 2 cities to build plants in? Or is that a different question? The question I answered was, given that I have a plant in Nashville, where's the best place to put a second plant? Is that the same as saying what's the best 2 cities? And so generally speaking, let me try this. I mean, you know, if this is my area, right? If I say, where's the best place to put a city, it's going to pick somewhere in the middle, right? And then if you say, okay, where's the next best place? I might put it over here somewhere. But if you just say, where's the best place to put 2 plants, it'll be maybe 1/3 of the way and 2/3 of the way, like that, right? So I did not really answer the question. Did not really answer the question where the best place to put 2 depots. All right. So that's where. So what I could try is I could try all possible combinations of 2 cities and pick the cheapest, right? That's one way to do it. So if I have n locations as possible places to put a plant, and I want to find where to were to put one plant, I have to try n locations. If I want to find the best for 2 plants, now basically I have to try n times n minus 1 over 2 pairs of locations and pick the cheapest. And generally speaking, if I had 3 depots and I had n cities, then it would be n choose 3 triples I'd have to try. And if I take this approach of trying all the combinations and finding the cheapest, well, you know, the number of combinations goes up pretty rapidly. So if I only have 10 customers, I want to put down one plant, I have to consider 10 different alternatives. But if I have 10 plants and 100 customers, then I have something like e to the power 13 combinations to try. So the approach of trying all of the combinations obviously won't work because the amount of work you have to do increases at an exponential rate. Right, so this is an example of the combinatorial explosion of possible solutions. And so the approach of trying every solution and picking the cheapest won't work when we face this combinatorial explosion. And this is tied up, if you've had computer science courses, talking about computational complexity of problems. Problems that are very hard to solve on computers are those that have at least this feature, that as the size of the problem increases, the difficulty increases, the number of solutions increase at an exponential rate. Okay, now this p median, so we already said that trying all possible combinations won't work, but there are obviously other approaches to solving this. And, you know, we can solve problems with, you know, with thousands or tens of thousands of nodes using these approaches. I'm going to skip that. And as you might have guessed, the approach for solving these problems is to use optimization. We can solve pretty big problems with optimization. Solver is not the greatest optimization algorithm in the world, but even with Solver, we can solve some decent sized problems. All right. So how are we going to approach this problem? So there's a bad way to approach it, although it's technically correct. And then there's a good way to approach it. So here's a kind of a straightforward formulation. We have a we have a variable y sub I that equals 1 if we have a plant in city I, and it equals 0 if we do not have a plant in city I. All right. So we have a constraint. We want to open exactly p plants. So when we add these up, they have to equal p, and the yi have to be 0 or 1. And now we have our demand weighted distances. And basically we have an objective function, and the idea of the objective function is that the cost of supplying a city from a particular plant, well, the cost of supplying a city from a plant is really high if we don't open a plant in that city. Okay, so if y sub I is 0, it's my cursor. If y sub I is 0, the cost of serving customer J from city I is some really big number plus Wij. Now, if there is a plant open, if this y sub I is equal to 1, then the cost of serving customer J from city I is just Wij because this term becomes 0. Okay. Oops. So the problem is, I believe, gosh darn it. So let's go and see what this looks like in Excel. All right, so I formulated it exactly like I said. Here's our distances. our demands, so our demand weighted distances, the WIJs. My decision variables are where to open a plant. Okay,
Professor, you're not sharing your screen.
thank you. Okay, now hopefully you can see it. All right, start over again. So I only have 8 cities here, but that doesn't matter. Here's my distances, here's my demands, my demand weighted distances, the WIJ, my decision variables, whether to open a plant or not. And I've decided I want to open 2 plants in this problem. And so here are my costs for serving Chicago from Miami, etc. So they're all really big now because they haven't opened any plants. But if I were to open a plant in Chicago, right, now the cost of serving all the cities from Chicago would just be the demand weighted distances, right? My solver formulation. Well, I'm getting ahead of myself. Okay. So then I pick the minimum. So I got to decide where am I going to serve my customers in Chicago from. So I pick the minimum of those in this column, right? And so if I were to open, say, another plant in Los Angeles, so now I have 2 plants, right? Then it would pick the minimum of this and this. The others are all really big numbers. And then that would be the cost here. So these are all minimums of each column, and then I add up all of these cells that are highlighted, and that's my total cost. All right, so the solver formulation is fairly straightforward. My decision variables have to be binary, 0s or 1s. The number of plants I open has to be equal to the number I want to open, which is 2, and I'm trying to minimize this. All right. Now the problem is that this is a nonlinear formulation. It's nonlinear because of this minimum function right here. Right? I want to pick the minimum of the entries in this column, and that makes it nonlinear. And that, in a nutshell, is why this is a lousy formulation. So I put 0s in there to start, and then if I go to solver, I pick the GRG nonlinear solver and hit solve. And one of the reasons I'm doing this formulation is I want to show you something. Oops. My bad. Got to go back to this. All right, so this should be an equal sign here. I forgot to change that. As we said, we want to open exactly 2 plants. Now let me try and solve it again. So it'll open 2 plants. All right. But notice what it says, solver found an energy solution within tolerance, all constraints are satisfied. All right, and it said open a plant in Washington and a plant in Dallas. Right? And I don't think I buy that. To me, that doesn't even pass the common sense test. Right? So let me think. I'm thinking, looking at these cities, thinking if I tried Denver and Washington, I get a way cheaper cost, right? So the point of this is that solver can be dangerous. So this cost is 438 or 4.3, 4.4 million. And remember what solver gave me. Gave me 5.4 million, right? So solver didn't work, but I don't even know it didn't work because it didn't give me any indication that it didn't work. All right. So that's a problem. Now, the problem was that that's a bad formulation and it's because of this minimum function here. Makes it nonlinear, and because it's nonlinear problems are just hard to solve. So here's a good formulation. I really like this formulation. I thought whoever figured this out is pretty clever. So we have one decision variable is the same as before. Y sub I equals 1 if we open a plant in city I. 0 otherwise. Then we have a second decision variable, X sub I(j) is equal to 1 if we serve our customers in city J from our plant in city I. And the key to this whole thing is this constraint here. This is Xij has to be less than or equal to Yi. So if Yi is 0, that means Xij has to be 0. In other words, if there's no plant in city I, we cannot serve a customer from city I. On the other hand, if there is a plant, if this is equal to 1, then we can serve customer J from city I. All right. This constraint says we open plants in exactly P cities. We minimize the weighted distances times, right? So if this will be 1 if J is served from I, and if J is served from I, it'll cost Wij. And then the Xij and Y have to be binary 0, 1 variables. And we have to serve each city, we have to serve each customer from one plant. Right, so this is a really nice formulation. That's this one here. But it's a little bit more cumbersome to do in Solver, all right? So far it looks the same. We have our demands, we have our distances, we have our demand weighted distances. We have our decision variables of where do we open the plants. And now we have more decision variables, Xij's, that would be 1 if we serve city J from plant I. So for example, this 1 here means we're going to serve our customer in Seattle from our plant in Denver because our plant in Denver is open, right? So we have to serve every customer from exactly one city. So when we add up each column, it should be equal to 1. So this row here is just the sum of those columns. And this is just a set all 1. So this column, this row here should be equal to all 1s here. Okay. And then to calculate our costs, basically, this matrix here says where we serve each customer from. This matrix here gives us demand weighted distance. So if we just do a sum product of this matrix and this matrix, it will give us the total cost, which is right here. Now let's look at the solver model. Well, and the thing I forgot to mention is the constraint that this Xij is less than Yi. So basically this column has to be less than or equal to this column. Also, this column has to be less than or equal to this column. Also, this column has to be less than or equal to this column, right? This is the constraint that the Xij's are less than the Yi's. So when we implement that in Solver, we have to do all of those columns independently. So it's kind of a pain in the neck. That's why there's so many constraints in here, all right? But all the constraints are linear, so we can use simplex LP to solve it. And it actually solves it pretty nicely. And so it says open plants in Denver and Washington. Okay. Now, this is an even better formulation. It's a little bit more complicated, but it saves all those constraints. It was actually Cecile's idea, so I'll give her credit for this. And we can actually go up to all 12 cities now. So it's exactly the same. Demand weighted distance matrix, the Yi's that decide whether we open a plant in a city or not. And these are the XIJs. Where do we serve each customer from? So what Sachil suggested is we add up each row and we divide by 12, right? So when we add up each row, notice that these are the 2 rows where we have plants in. So when we add up each row, it'll either be 0 if we don't open a plant, or it'll be some number greater than 0, right? In fact, you can think of these numbers as the fraction of cities that we supply from, in this case. So we supply 58% of the customers from Atlanta and 41 from Salt Lake. But the point is that if the plant's not open, this has to be 0, right? So the way we implement that, oops, that's not what I wanted to hit. We have this constraint here. It says that these numbers here have to be less than or equal to these numbers here. Oops, these numbers here. So if I have a 0, the plant's not open, then this has to be a 0, right? But if this is a 1, then I can serve customers from those cities. So it's a trick that basically makes the solver formulation easier. Okay, again, this is a linear problem. Okay, and so it tells me to open plants in Atlanta and Salt Lake. Suppose I wanted to open 4 plants instead. I make that 4. Now I can run it. See how long it takes. This is an integer programming problem. They're not trivial. So now we're opening a plant in Salt Lake, Nashville, Washington, and Miami. Okay, interesting. All right, so I kind of buried some of the features of this formulation. One of them is that we're assuming that it's free to open a plant, right? Where in this formulation does it say it costs money to open a plant? Okay, another thing I buried is I buried the fact that we're allowing the plant to supply as much as we want to. In other words, there's no capacity on that plant. So there's 2 big problems with this formulation. We assume unlimited capacity in each plant, and we assume plants are free. So we're going to try to deal with those bad assumptions one at a time. And the first one is that we're going to now charge for our plant, all right? So now if we open a plant, it costs us money, just like it does in the game. At this point, we're still assuming it's an uncapacitated problem. In other words, each plant has unlimited capacity. So the formulation looks just like the last one, except we add on this cost for opening a plant. So if you open a plant in city I, yi is 1, and we get charged whatever this amount C is. All right. And now instead of this being equal, or we say we want to open exactly P plants, we say we're going to open up to P plants. But now it's going to pick how many plants to open. Because, you know, since they cost money, we might not want to open a whole bunch of them. All right, so that's the fixed charge problem. It looks exactly like the one we just did. The only difference is that there's a less than or equal to constraint on how many plants we open. And I have my total transportation cost, which is the same as before. That is the sum product of the yellow matrix and the weighted distance matrix. Now I'm going to add in a cost of $140,000 per plant, right? For each plant that is open. So I add the transportation cost and the plant cost to get the total cost. That's what I'm trying to minimize. Right, so that's basically all I did was add in that cost. And I made it a less than or equal to 4 plants, okay? So I kind of owned up to the 2 problems that plants cost money and plants have capacity. The other thing I mentioned earlier, but I want to point out again, is that we assume we know the demand, right? That's assumed. So in this case, it opened 4 plants. What is it? Miami, Washington, Nashville, and Salt Lake, right? Here were the demands I used. You'll notice that they're pretty high demands. Suppose I picked another case, right? Where demands were, say, lower, so I'll just copy and paste that into here. So now a case with smaller demand. Now if I go to solver and solve it again, I'm expecting a somewhat different solution. All right, so now it only opened 1 plant, and that plant was located in Nashville. All right. So if I have a really high demand, I'm going to spend a lot of money on transportation, and it might behoove me to open more than 1 plant. But if I have light demand, right, then the transportation costs are not too high, and I want to keep my plant costs down. Okay, so that's what we're seeing there. All right, so we handled the problem of plants being free. Now, what about the fact that plants have capacities? Okay, so that brings us to what's called the capacitated facility location problem, where each depot or each plant now has a capacity limit. All right, so before, we knew that each customer would be supplied from exactly 1 plant. Why is that? Well, because if there are no capacity limits, you'll always serve the customer from the closest plant, right? But now with capacity limits, that's not true. You might be forced to serve a customer from 2 different plants because you might run out of capacity at the closest one. So that's the wrinkle that this one serves, or this one presents. All right, so this is our formulation for capacitated facility location. Oops, I should have not gone away from this so quickly. So now the formulation has to change a little bit. Before, Xij was a binary variable that said, do we serve city J from plant I? So now what we're going to change the formulation, is change the decision variable. So now Xij is the fraction of the demand in city J that is served from our plant in city I. So now this is a fraction between 0 and 1. And so SI is the demand in the city, Dij is the distance, C is the cost of opening the plant. Now we're going to have some capacity on each plant. Okay. So SI times Dij is just the Wij, the demand weighted distance. That's the same. This is the cost for opening the plants. Now it's still true. So this is the fraction that we serve. If there's no plant, the fraction has to be 0. Okay. Now this constraint says that we have to meet all of the demand in city J. Right. So if we multiply the fraction supplied from city I times the demand, add those all up over all the plants, and this says we have to meet all the demand in city J. If we sum over J, these are all the customers supplied from city I, from plant I. That has to be less than our plant capacity. Now the Yij still have to be 0, 1 binary, but now the Xij are real numbers between 0 and 1. Okay, so the formulation is pretty much the same. We have our distances, we have our demands, we have our demand weighted distances. We have our decisions where we open plants, yes or no, YI to YIs. So one means we open a plant in Atlanta and Salt Lake here. Now, instead of do we serve the customer from the plant, we have the fraction served, right? So for example, for Chicago, 61% of its demand is coming from our plant in Atlanta, 39% from our plant in Salt Lake. All right. Other than that, it's just the same as the last problem. The transportation cost, we have to, I guess, multiply. No, that's still okay. Yeah, so it's still the sum product of the yellow matrix times the weighted distance matrix. And you may notice that I multiplied up here by 0.005, that's the mileage cost. I multiplied it by 12 for 12 periods in the game, just to make it more realistic. All right, 140,000 for each plant, add all the costs up. And if I make these 0 and 0, and let's try solver. Again, everything is linear, should solve fairly quickly, hopefully. So we got a solution. Again, I point out that it's dependent on the demands I'm assuming. If, for example, I were to put a really high demand in LA compared to before, it will likely change the solution. Okay, so now it actually opened 4 plants, including one in LA, one in Denver, one in San Francisco, one in Atlanta. All right. So this is almost the problem. Well, this is pretty much the problem you need to solve in the game. The only thing is you have to kind of know what your demands are going to be. But if you can make a plan for how much you'd like to sell in each city, in each period, then you can get a good idea of where you should locate your plants. All right, so what if we assume that the plants can go anywhere on the map, right? They don't have to be at one of the cities. So this is really, this is an interesting problem too. It's been well studied. So each facility, well, so each city, each blue dot has a demand W. Their end customers. Facility can be located anywhere in the plane. The distance from the facility to the customer is calculated based on Euclidean distance, which may or may not be a good assumption if you're using roads. The total cost for a customer is the distance times the weight. Same as before, weighted distance. Okay, this problem is known as the Weber problem. It was published over 100 years ago. And people speculate that Fermat might have actually posed this problem too. If you are into statistics, you can think of it as a 2-dimensional median if you wanted to. Okay, so the idea is we have the coordinates of each city I, X and Y coordinates of city I or AB, AI, BI, and then you have to decide the coordinates X, Y of where to put the facility. Okay. So this will give us a distance from each city to the depot. And by the way, the decision variables are what should be X and Y. The AI and the BI are known data. So this square root thing, that's the distance from the plant to the city multiplied by the weight. And there's no constraints. However, it is a nonlinear problem. As you can see, we got some squares in there and some square roots in there. And so you might ask the question, how come the answer is not the center of mass, right? So if we view each one of these dots as having a weight, right? And we could compute the center of mass of all of these weights, and why wouldn't that be the answer? And the answer to that question is that if this were the problem we were solving, note the problem we were solving has a square root in here, right? So if we got rid of that square root, then we could solve this problem by calculus, which I did. And in fact, we end up with the center of mass. So the center of mass will solve the problem of minimizing the weighted squared distances, not the weighted distances. So the center of mass is not the solution to this problem. Now the Weber problem, which does have the square root here, so have it to the half power, you can find the partial derivatives, but if you try and set them equal to 0 and solve, you will in fact be out of luck and it won't work. But we can clearly solve this in Solver, okay? So here are we have 20 cities. Each city we have X and Y coordinates for. And for each city we have the demand. And these are our decision variables, the X and Y coordinates of the depot. I can start them off at 0, right? And then here I just computed the weighted distance from the depot to the city multiplied by the demand. When I add them all up, when I add these all up, that is my objective function. So the solver model is pretty easy, no constraints. Change 2 variables, objective function. And there we go. So solver can solve this problem pretty easily. What about a one-dimensional Weber problem? So imagine that all of the cities are located on one highway and we want to decide where to put the plant. And so it's one-dimensional. You think of all of the cities being located on a line. So now we could formulate the problem this way. This would be the distances. Oh, I didn't multiply by the weights, but that's irrelevant. Because the point I wanted to make is this equation equal to this equation? The answer is it is not. You have to consider absolute values, right? And once you consider absolute values, you can't take the derivative. And so you cannot even solve the one-dimensional problem with calculus. So we're out of luck. All right, so setting the derivative equal to 0 and solving doesn't work. We need another approach, which you guys get to figure out because that's one of the problems on the homework. Some thinkers in the past have come up with some interesting ideas. If we have only 3 cities, some guy came up with this idea. So you draw a line between the 2 cities, make it an equilateral triangle. You draw the circle that inscribes that equilateral triangle. And you do that for all 3 edges. And then where the circles meet is called the Torricelli point. And that turns out to be the solution to the problem. Don't ask me why. If you only have 3 cities, you can do it that way. Some guy named Varignon came up with this idea. He said, okay, if I drill holes where each of the cities are, and then I attach weights to strings. So I have a weight attached to a string going through each hole, and they're all tied together. And there's no friction or anything. And you ask, where will the knot settle? The answer is the knot will settle on the solution to the problem. That's kind of interesting too. Well, maybe it is, maybe it isn't. I don't know. All right. So one more problem to show you. What if I wanted to put down 2 plants anywhere in the plane? All right. So now I have my location of the first plant, my location of the second plant. And so I find the weighted distance from each plant to the city, and then I take the smaller of the 2. So this is a minimum of these 2 weighted distances. Then I add these all up, and that's my objective function. And so this is still a nonlinear problem. Interestingly enough, it is actually not even a convex problem. That means that wherever I put in what I put in for my initial solutions will affect the algorithm. So if I start with both deep, if my starting solution is both depots are at 0, 0, and I try and solve it, I get this solution, which I think is probably not very good. If I started out at, so just remember what the solution was. 21,000 roughly, okay? If I started here at some other place, and I solve it. Damn, I got the same solution. Now let me try this one. Oh, crap. Okay, I think I know what I did wrong. Aha, it's already solved the problem. There's this thing for GRG nonlinear, there's this option called use multi-start, all right? So I should have had that unchecked, okay? So that would be how you normally do it. So if I start at 0, 0, and I run solver, okay, now it doesn't give me the optimal solution, right? It gives me something different. If I put it here to start with, okay, it gives me a slightly different solution, all right? Remember on last week where we had that objective function that was like wavy, like a bunch of local optima? This problem has that same feature. So what the GRG nonlinear solver allows is you can, sorry, this one here, use multi-start. So rather than starting from a fixed point, climbing to the nearest hilltop and stopping, it will try many different starting points. From each of those many different starting points, it'll climb to the local hilltop, and then it will tell you whichever is the best solution. So this is another way to deal with those non-convex problems, and this gives us the right solution, okay? So actually, I thought that's kind of interesting. All right, so that's what multi-start is. Okay, I've talked far long enough. There is an assignment due for next week. And once again, the decisions are due the same as always, early next week, last period of the practice round. Does anyone have any questions? So chill, it's a little early for beer.
Yes.
No?
No, this isn't beer. This is just mineral water.
I'm just kidding. Does anyone have any questions? Because when we're done with questions, Sachil will send you all to your team breakout rooms, which hopefully work. And if you need us, you should be able to call us from your breakout room to come help you with questions. All right, I'm still not hearing any questions, so I guess, Sachil, you can send them to the breakout rooms.